So if we look first at the mechanism for the imine formation, we have a ketone undergo a reaction with a primary amine. That means that our product is going to be an imine. This carbon of the carbonyl is this carbon of the imine. That is where all of the chemistry takes place. You should be able to work through this mechanism on your own. So what I want you to do is to pause the video and try to work through the mechanism. So what we know is that any carbonyl, like this ketone, has resonance. And so the resonance structure for that carbonyl looks like this. In this reaction, what has also happened is that all of this acid that we added has already reacted with this amine. So rather than having an amine, an H3O plus present in our reaction, what we really have is an ammonium ion. And remember that we have been very careful with the amount of acid that we've added, such that all of the amine in our reaction has not been converted to that ammonium ion. So we have an equilibrium between this amine and this ammonium ion in the reaction. So one of the things that can happen in this reaction is we could have our amine directly attack that carbon of the carbonyl. That is a valid first step. Even though this reaction takes place under acidic conditions, that amine is capable of directly attacking that carbon of the carbonyl because it is such a good nucleophile. With the emphasis that we've placed on oxygens picking up protons under acidic conditions, I also find it acceptable for you to protonate this oxygen from either your ammonium ion or that H3O plus in the beginning of your reaction. The choice is yours. You'll see both ways. So in this reaction, that oxygen can pick up a proton from the ammonium ion, give the electrons back to the nitrogen. So when that oxygen picks up a proton, we get this structure. That means that my amine can act as a nucleophile toward that carbon and give me a tetrahedral intermediate. I'll need a base for my reaction to remove one of these protons so as to keep that carbon-nitrogen bond intact. And the best base that I have in my reaction is going to be a molecule of my amine. So that can grab one of those protons and neutralize that group. So now my tetrahedral intermediate looks like this. So as we look at the product of this reaction, we see that we need to make a carbon-nitrogen double bond. So we're going to need to get rid of this oxygen. We know that anytime we have acidic conditions, we can get rid of an oxygen-containing group through protonation. So we're going to have our OH pick up a proton from either an ammonium ion or a molecule of H3O plus, pick up that proton, give the electrons to the nitrogen, and that's going to give me a molecule of water that's going to be able to act as a leaving group. So now this is the tetrahedral intermediate that can collapse. This tetrahedral intermediate can either collapse by the water group falling directly off to give me a resonance stabilized carbocation, or this tetrahedral intermediate can collapse where the lone pair on the nitrogen is going to help push out that molecule of water and give me this intermediate. So as my tetrahedral intermediate collapsed, I formed my carbon-nitrogen double bond and I lost a molecule of water. Now, in this reaction, the last step that I need to do in order to form my final product from this intermediate is that deprotonation. So I'll need a base in my reaction, like a molecule of amine, to remove that proton, give the electrons to the nitrogen, and that will give me my final product. My final product in this reaction is the imine functional group. Remember that this is a reversible reaction, so each of these steps are going to be driven by equilibrium. And we'll talk about the reverse mechanism in a little bit. So this is the mechanism for the formation of the imine from a ketone and a primary amine. So the next reaction that we're going to look at is the reaction of an aldehyde in the presence of a secondary amine to make an enamine product. You should be able to work through this mechanism on your own, so pause the video and work through the mechanism. Remember that all of the chemistry is going to happen at this carbon of the carbonyl, and it's this carbon of the enamine that is that same carbon from start to finish in this reaction. So overall, we could start this reaction by a protonation of the aldehyde with the acid in our reaction, or we could also start with a direct attack by the amine because it's a good nucleophile. Remember, the pH is carefully balanced such that all of the amine in this reaction is not protonated. So in this reaction, I could have my amine start by attacking at that carbon, and that looks like this. So that in this reaction, I have a negative charge and a positive charge. And we don't usually draw negative and positive charges like this. And under the conditions of this reaction, remember we do have an excess of protons. So if one of these charges is going to be fixed first, it's highly likely that it's going to be this charge. So I'm going to pick up a proton from a molecule of acid. And that's going to give me this intermediate. Now I still have a charge, so now I need to fix this charge, so I'll have a molecule of amine that can come along and remove that proton and neutralize this tetrahedral intermediate. So now I have a neutral tetrahedral intermediate, and if I look at this tetrahedral intermediate and compare it to my final product, I see that I need to get rid of this carbon-oxygen bond and I need to keep this carbon-nitrogen bond intact. So in order to help me get rid of this carbon-oxygen bond, what we're going to do is protonate, just as we've done since the very beginning of this semester for oxygens that are under acidic conditions, even if it's not strongly acidic conditions like we have here. So I have a molecule of H3O+, and I'm going to pick up a proton, and that's going to set me up to have my tetrahedral intermediate collapse because I now have a molecule of water that can act as a leaving group. So I now have a molecule of water that can act as a leaving group. My molecule of water can take its electrons and fall off. And if it does that, I get this. This carbocation is resonance stabilized. I can use this lone pair to stabilize that carbocation. And that would give me this structure here. Now we saw a similar intermediate to this one in the mechanism of the imine, where our nitrogen had a positive charge and a double bond to the carbon. In the mechanism for the imine, we were able to fix that charge on the nitrogen through the removal of a proton. In this structure, in the formation of the enamine, the difference in the mechanism arises from this step. This nitrogen, we can't fix its charge. So whenever we have a positive charge, the pKa of the protons on the adjacent carbon, so this one here, The pKa of these protons are going to drop dramatically because of the stress and the charge on this intermediate that we have. So the original carbocation was here. We can resonance stabilize that carbocation with the nitrogen, but that's not going to lead us to the product in the same way that we saw in the imine mechanism. So what's going to happen is a base, like a molecule of water or a molecule of amine, is going to come along and remove one of these protons, send the electrons towards the carbon, send those electrons back up to the nitrogen, and what's going to happen in that case is the formation of my enamine. And my enamine product looks like that. Remember that the enamines form when we have secondary amines. My secondary amine starts with just one proton, and I lose that proton from the amine once I make my carbon-nitrogen bond in this step right here. From then, through the rest of the mechanism, my nitrogen no longer has any additional hydrogens, so in order to keep that bond intact and neutralize the charge, I have to form that double bond. Notice that in the case of the imine formation, my nitrogen had two protons at the beginning of this mechanism. I removed the first one once I formed my tetrahedral intermediate, and then I was able to remove my second proton when I had this resonance stabilized carbocation here, and that led me to my imine product.